Okay, welcome to the review sheet video for not clipping, for the section 4.3 quiz. Okay, so we'll start out small here in that these first questions are just basic simplifying radicals. And if you know how to do this, you should be okay for the rest of the material in that every single piece of material after this involves simplifying a radical. So this is just a standard simplification of, whoops, oh, yeah, why is this? Oh, my pad's upside down. And we're back. Okay, so we look for the greatest perfect square factor of 150. Now, I'm going to say this a couple of times over, but I think it's beneficial just to be clear about this for the first problem. You're all going to have calculators for this quiz. That being said, if you write down the perfect squares, so 4, 9, 16, this is just the list of perfect squares. 2 squared, 3 squared, 4 squared, 5 squared, 6 squared is 36, 7 squared, and on and on and on and on. Basically, what you want to do is you want to, in your calculator, take the radicand, 150, and then systematically divide over and over and over again, 150 by these perfect squares. It's say, I divide 150 by 4. My answer is not going to be an integer. It's some decimal. So I know that 4 is not a factor of 150. 150 divided by 9. That is also not a decimal, and on and on and on. Now, my first result here when I divide 150 is going to be, so I'm taking my calculator and I do 150 divided by 25. My first result, that's an integer, okay, is 6. So I have a factor pair of 6, and I'll write it just in terms of a coordinate point of 150 as 6 and 25. How do I know that this 25 is um, the greatest perfect square factor of 150? Here's how. It's pair 6. If 6 does not have any other perfect square factors, and it does not, there are no perfect square factors of 6. 6 does not divide 4, 9. Of course, 9 wouldn't divide as well, too. It's obvious 6 does not. If that's the case, we've identified the greatest perfect square factor. So we'll go into, this is not a good example that has multiple perfect square factors before the greatest one, but we'll go into another example that has this in a second. So because I identified, that is when I say this, another perfect square factor that's less than 25, but we should be able to identify when it's not the greatest perfect square factor easily. Okay, so 25 is the greatest perfect square factor. As a result, root 150 breaks up into, so this is equal to 25 and root 6. Root 25, or the square root of 25, is 5. So I have 5 times root 6, which we just write as 5 root 6, if we know how to write a 5. Final answer. Next one, square root of 80. Okay, so square root of 80. We are trying to identify the greatest perfect square factor of 80. And here's where what I was talking about from the last problem sort of comes into play. We are listing all the perfect square factors, 4, 9, 16, 25, 36, etc. Okay, so 80 divided by 4, right? Everybody knows that's 20. So a factor pair of 80 is 420. Okay, now 4 is the perfect square here. Is it the greatest perfect square factor? It is not, because 4's factor pair, 20, also has a perfect square factor. It happens to be 4, but for that reason, we know we need to go on and say to ourselves, okay, no, there's a greatest perfect square factor that's greater than 4. It happens to be 16. Okay? Because we divide 8 divided by 6. We put in our calculator 8 divided by 16, and we get 5. So we know that also 16 and 5 is a factor pair that we're dealing with. So I hope everybody is following that. We went into that a little bit today in the do now, as well as during the review with the group that was with me. and after school with some students too. But I just want to be clear on that. We're using our calculators effectively as tools to be able to simplify these radicals, and that I'm just literally doing 80 divided by 4, 80 divided by 9, 80 divided, oh, that doesn't work, 80 divided by 16. Oh, well, I have 4 and 20, but I know that 4 is not the greatest perfect square factor because 20 has a perfect square factor. So then I move on to 16. So 16 happens to be that. So for that reason, we divide 16 and 5. Root 16 is 20. Final answer, 4 root 5. Next. Negative 7 root 28. First one, we have a coefficient to the radical. But just treat this as a product of negative 7 and then the simplified whatever the square root of 28 is. The greatest perfect square factor of 28 is 4, so I divide this up into negative 7 times root 4 times 7. So final answer, negative 7 times 2 times root 7. This 4 just turned into 2 here. So I'm getting negative 14 root 7 is my final answer. Okay. 8 root 30. 8 is just a multiplier on the end here. Square root of 30. Does that have a perfect square factor? Let's see. Does 30 divided by 4? No. Divided by 9? No. 16? No. I can once again check this on my calculator. It turns out, whoops, 8 root 30 is my final answer. This is fully simplified. And there might be questions like this in the test. So don't crack your head and say, no, I have to be able to simplify this. No. 8 root 30 is fully simplified, and that the square root of 30 does not have any perfect square factors. So once again, I mean, we can just do this from our calculator. We say, okay, 30 divided by 4. No, that's not going to work. That's some sort of decimal. Okay, so it's 7.5. But okay, 30 divided by 9. No, that's some sort of decimal. That's not going to work. 30 divided by 16. That's not going to work, right? That's also some decimal. We don't need to go on because we know if we get to a perfect square that's half of 30, 2, at the very least, 2 has to be its factor pair. And there's no way that, for instance, 36 is a factor of 30, which is the next, or 25, I should say, and then 36, which are the next two factors. So for that reason, we say, okay, all these produce decimals, so 8 root 30 is my final result. 180, root m root n. Okay, so, or I'm sorry, the square root of 180 mn. So, square root of 180. Our first step here is to, when we're simplifying radicals that have variable components, is to divide these up into their respective products. There's 3 products here, root 80, root m, and root n. Let's deal with root 180 first. So it happens to be, and I can decipher this from my calculator, but note that if I am factoring 180, right, and then I'm dividing 180, and I take 180 divided by 9, let's say. 180 divided by 9 is 20, so we know that there's a factor pair of 9, 20, and that 9 is a perfect square, and 20 is its factor pair. But since 20 also has a perfect square factor, there's one that's greater. So we discover that actually 36 is the greatest perfect square factor in that 36 and 5 is the factor pair we're dealing with here. So root 180 divides into root 36 and root 5. Okay, now root m and root n. I emphasized this in class when we were going over this material, but if there is an exponent of 1 in that both m and n are raised to the first power in the radicand, there's no way to simplify this. We cannot take the square root and break apart m or n if it's just the exponent of 1. So for that reason, root m and root n are fully simplified. So any variable underneath the radical or a variable in the radicand that has this exponent of 1, fully simplified, we can't do anything to it. So for that reason, these just carry through, root m times root n. Root 36, that's just simply 6 times root 5 times root m times root n. Okay, so my final result, once I simplify all of these products, and that I have 4 of them here, is to just simply take all of the products that are not underneath the radical. In this case, it is just the product here, 6, that I'm circling in blue. Take all the products that are underneath the radical. These 3. Okay, I'm taking my green guys. Move back to black ink. I'm taking my blue guy here, and I am multiplying. It only happens to be one of them, but if I had more, they would multiply to be the coefficient of the radical. So that's just 6. 5, root 5 times root m times root n is just all of those 5 times m times n underneath the radical. So my final result, 6 root 5mn, my final answer. Okay. 11. Root 392 root or square root of 392 x to the fourth y to the second power. So I'm breaking these up into my 3 separate radicals that I'm simplifying. 392, not an easy radical to simplify. When we go through our process, we can see that in the calculator that 14 squared, or 196, is the greatest perfect square factor. 392 has other perfect square factors, but we would look at its factor pair, say, does that have any perfect square factors? It does up until 14. So for that reason, 392, when I'm trying to factor it here, I'm saying, okay, my greatest perfect square factor is 196. Its factor pair is 2. So I'm breaking up 392 into 196 root 2. Now, anytime that I have a even. So this this I think was what students were struggling with a lot here. Simplifying variables with exponents that are underneath the radical and decide how do I simplify these individually. Okay, so let's break this down for this one. If I have an even exponent, okay, it still follows the rule that we're going to go into in odd exponents, but anytime I have an even exponent, and let me sort of go here with this. Anytime I have an even exponent, like square root of x to the fourth, all I'm doing is just dividing my exponent, in this case 4, by 2, putting my answer as the exponent and eliminating the radical. So that is the square root of x to the fourth is x to the second power. So these results apply. What is, oops, go back to my pen here. What is, let's say, we'll write down the square root of x to the eighth. Well, that's just 8 divided by 2 is 4. X to the fourth. What's the square root of x to the 16th? That's x to the eighth. What's the square root of x to the 32nd power? Well, that's just x to the 16th. What's the square root of, you'll see this can just go on and on and on and on. Well, we have what's the square root of x to the 12th? That's x to the 6th. On and on. Okay, so anytime you have a even exponent, you are just dividing that exponent by 2 and then removing the radical. Okay, odds are a little different, and let's deal with these individually. In fact, we'll show odd in another problem when we actually have an example. So both of these are even. So we know for sure that what's square root of x to the fourth? X squared. What's the square root of y squared? Y. We can put the absolute value sign around it now if you like. You can also do that at the end. The reason why we put the absolute value is because y has an odd exponent. So next step, we want to identify, and once again, I'll circle, okay, no, sorry, 196 can be simplified to 14. So we have 14 times root 2 times x squared times absolute value y. We are now identifying which of these products, there's 4 of them here, and once again, I'll circle in blue, are in the coefficient that are not underneath the radical anymore. 14, x squared, absolute value y. And I'm going to circle in green ones that are underneath the radical. Square root of 2. I multiply my blue guys first and make that as the coefficient to the radical. So 14 times x squared times root y is, sorry, absolute value y is 14x squared, absolute value y. What do I have as my radical? There's only one left. There's just the square root of 2. If there was another radical, that I'd be multiplying root 2 by something, but for that reason, my answer is just root 2. So final result, 14, x squared, absolute value y, root 2. 13. Once again, just breaking this into products. Negative 8 times root 18 times h to the fourth. Square root of h to the fourth times the square root of j to the fourth times the square root of k to the third. So now we have our first odd exponent. So we'll deal with this off to the side when we get to it. Negative 8 stays the same. Root 18, greatest perfect square factor is 9, so that splits into root 9, root 2. H to the fourth, divide 4 by 2. My answer is 2. Get rid of the radical. H squared times j squared. Okay, so if there is an odd exponent, and this is where we were using quotients and remainders and so forth. I'm taking my exponent here, 3, dividing by 2. My answer for that using quotients and remainders is 1 remainder 1. So what do? I write k, k root k here, and then I'm placing in these circles here and here, okay, exponents that represent the quotient and the remainder. The quotient is the exponent of the coefficients variable, 1. The remainder is the exponent of the radicands variable, 1. So my final answer is k root k, or I should say absolute value k root k. Note this, the remainder is always 1, and what's underneath the radical, that variable always has an exponent of 1. Always, always, always. So we went through this pattern in class, but just note that. And let's look at another example. What is absolute value x to the fifth? Well, if I divide 5 by 2, my answer is 2 remainder 1. 2 is the exponent of the coefficient variable, x squared. 1 is the exponent of the variable that's underneath the radical of the radicand. So it's always going to be root x. What about, let's say, x to the 7th? Well, that's simply 7 divided by 2 is 3 remainder 1. So my answer is x to the 3rd root x. So it's always going to be, so this is that. It's always going to be root x. So the exponent to the variable underneath the radical is always, always, always 1. So let's take another one. What about the result? The square root of x to the 19th. Okay, what's 19 divided by 2? Well, that's simply 9 remainder 1. So what's this result? X to the 9th power, okay, root x to the 9th, because 9 is my quotient, to the 1st power, because 1 is my remainder. So 1 will always, always, always be the remainder. Keep that in mind. This is an important result. Okay, so, and also, these just keep repeating that any variable to the 3rd power, simplified, is just going to be, in this case, k root k. But in x to the 3rd power's case, the square root of x to the 3rd power, it's x root x. What's the square root? And I'll write this on the bottom here. What's the square root of m to the 3rd? Well, that's just m root m. What's the square root of a to the 3rd? A root a. So you see the pattern. Anything that's the 3rd power is that letter root the letter. What's the square root of z to the 3rd? Well, that's just z root z. So that's maybe something that you can memorize. Not saying that that's an amazing thing to do, but that's possible if you want to think about it as a pattern. So root 9 is 3. Root 2 stays. H squared stays. J squared stays. K root k. You want to think about this as k, this is a product, times k times root k. So you want to break these into the two products. And the reason why I do that is because when I circle my my products that are not underneath radicals, I'm splitting up k and root k. One is and one isn't, meaning that root 2 does not apply. J squared does, k does. My products that are underneath radicals are root 2 and root k. So I'm multiplying all of my blues here, to make up the coefficient. Negative 8 times 3, negative 24. H squared, J squared, absolute value k, root, what's 2 root 2 times root k, root 2k. Okay. This is my final answer. Okay. Last one like this. I believe that's the last one like this. Yes. Okay. So we have root 2 times, or sorry, negative 2 times root 45 times, sorry, not absolute value, root x to the fourth times y squared times z. Okay, so we know all our results here very quickly. I'm going to buzz through this one. In that negative 2 times 9 is the greatest perfect square factor of 45. Root 9 times root 5. X to the fourth is x squared. Y is square root of y squared is absolute value y. And then the square root of z stays. We don't need to change that. So this becomes negative 2 times 3 times root 5 times x squared times absolute value y times root z. Now I'm not going to circle with blues and greens. I'm just going to simply identify visually what's underneath the radical and what isn't. We have negative 2 times 3, negative 6. So I'm crossing that out, crossing that out. And this is good notation. If you're not going to circle in blues and greens, it's a good idea to cross stuff out. Times x squared. This is a product here. So that's not negative x squared. Just note that. So it's negative 6x squared. Cross that out. Absolute value y. Cross that out. And then my two products that are underneath radicals, 5 and z. So 5z. Final answer, negative 6x squared, absolute value y 5z. Okay, new type of problem. The sums and differences of radicals. First step here is to always just simplify all these radicals individually. So I look at these three separate terms, negative 3 root 6, negative 2 root 6, and 2 root 54, and decide if I can simplify them at all individually. Okay, negative 3 root 6, no. 6 does not have any perfect square factor, so these are both cannot be simplified. 2 root 54, yes. 2 root 54 simplifies into 2 times the greatest perfect square factor of 54 is 9. And the, what's it called? Its factor pair is 6, so that's square root of 6. So this becomes 2 times 3 times root 6, which is equal to 6 root 6. So when I rewrite this, this is sort of this term's work over here. I can rewrite this as negative 3 root 6 minus 2 root 6. I just carried through those first root terms plus 6 root 6. These are all like terms. How do I know? I emphasize this by circling in blue. They all have a root 6. I cannot add or subtract terms unless they all have the same radical components. So they all are root 6, meaning that I can feel free to add or subtract them. How do I do that? I do that by physically adding and subtracting the coefficients. Negative 3 minus 2 plus 6. Now, my suggestion would be so I'm going to rewrite this problem here. Negative 3 minus 2 plus 6. You don't have to rewrite this. My suggestion would be to do this on your calculator that I'm going to provide to you, because I think adding and subtracting positive and negative integers is somewhat of a struggle for some students. Don't let this work trip you up. Just use a calculator. Literally plug in negative 3 minus 2 plus 6. It happens to be negative 3 minus 2 is negative 5 plus 6 is 1. So for that reason, we have root 6 is my final answer. But don't let this work trip you up. This is, if you need to do negative 3 minus 2 plus 6, then that's what you need to do. That's totally fine. Final answer, root 6, because this answer here is 1. I don't write this 1 as a coefficient. I just write root 6. Next, 2 root 24. The greatest perfect square factor of 24 is 4. So that splits up into that product there. And I'm just going to rewrite 2 root 6 minus 2 root 6. Those cannot be simplified. So the only term that I'm simplifying here is 2 root 24. So this turns into 4 root 6 once this is 2. So 2 times root 6. 4 root 6 minus 2 root 6 minus 2 root 6. What's that? 4 minus 2. These are all root 6s, so I can feel free to add all of them. 4 minus 2 minus 2. 0, root 6, but we don't write that. We just write 0. Anytime you have 0 as a coefficient to a radical, this is 0 times root 6, which is 0. Final answer is 0. 21. A little bit more difficult in that these can all be fully simplified. So I'm going to simplify them individually and put those results in parentheses. -5. The greatest perfect square factor of 28 is 4, so that's root 4 times root 7, plus the coefficient 5. The greatest perfect square factor of 20 is also 4, root 4 times root 5. 5 is its factor pair. And then negative, oh, that's not a positive. That is a negative. Let me rewrite. Whoa. Let me rewrite all that. So this is root 5 minus the square root of 80. What is the greatest perfect square factor of 80? Turns out that 4 is a perfect square factor, but it's not the greatest one. Because I would do in my work, I would say, okay, 80 divided by 4 on my calculator. Well, that is equal to 20, so my factor pair is 4 and 20. But is 4 the greatest perfect square factor? No, because 20 has a perfect square factor as well, too. So we would continue to divide, and we would say, okay, 80 divided by 16. Oh, 5, that's an integer, too. So the factor pair that I'm looking for is root 16 times root 5. Okay, so let's simplify these individually. This becomes 2. I'm not going to rewrite these. I'm just going to cross it out and put it. That is 2. Root 16 is 4. So for that reason, this is -5 times 2, root 7. -10, root 7. 5 times 2, root 5. So that's plus 10, root 5. And then here, just simply minus 4, root 5. Okay. These two terms can be added together because they are both root 5. This is a root 7, so it may not. So I'm going to underline in blue the sets of like terms here, and then underline in green like terms. So these two underlined in blue are like terms. The ones in green are not. So my final result here is -10 root 7. All I did was just carry this down. And then what's 10 minus 4? 6 plus 6 root 5. Final answer. Okay, same sort of result. This is 5 times the greatest perfect square factor of 45 is 9. So root 9 times root 5. 3 root 3 cannot be simplified, so I'm just writing that to carry it through. Root 45 is once again root 9 times root 5, so I'm rewriting this. 3 and 3. 5 times 3 is 15 root 5. Carry down the 3 root 3. This is 9 root 5. So my result here, because I know that only 15 root 5 and 9 root 5 can be added, 3 root 3 cannot. So my final result is 24 root 5 plus 3 root 3. 15 plus 9 is 24. Root 5, keeping the root 5 here. So when I'm adding these radicals, I'm keeping the radicand and just adding the coefficients. 3 root 3 cannot be added, so that is left as two terms, 24 root 5 plus 3 root 3. Okay, products. I think these are actually the easiest ones to do, for sure. How do I do this? I just multiply my coefficients. I wrote this 1 in here so you would know, but I'm multiplying coefficients, and that this is 1 times -5 root, multiplying my radicals, 3 times 10. And then I just simplify my result. What's 1 times -5? -5. What's 30 times 10? 300. I think I said 3 here, but that's 30 times 10. What's the greatest perfect square factor of 300? 100. So this is -5 root 100 times root 3. Root 100 is 10, so this becomes -50, or -5 times 10 root 3 is my final answer. Okay. How do I multiply these products? This is 1 times 1, but so we don't need to multiply coefficients at all. We just multiply the radicals. So 12 times 3 is the square root of 36. Now this is a sticking point here. Note that when you're simplifying a radical, make sure that you identify a perfect square when it's present. If this is just the square root of 36, that's just simply 6. This is easy to see when we're breaking apart radicals and we're simplifying the perfect squares underneath the radicand. But the square root of a perfect square is an integer. We don't need to break this up. In fact, it's incorrect to start breaking this up. If it's already a perfect square, we just take the square root. My final answer to this one is 6. Okay. Yeah. Okay. 29. All right. So, couple of things you can do here for these problems that involve rationalizing the denominator. We want to remove the radical from the denominator. I'm going to do the first one here using sort of one method and then show you a different one. All I'm doing in most cases, if the numbers are easy enough, is just multiplying by the radical in the denominator and in the numerator. So sorry, and I said that confusingly. I'm multiplying by the radical in the denominator, and I'm taking that radical, root 6, and making it a fraction that's equal to 1 by putting it over itself and multiplying by that fraction. So I'm multiplying by root 6 over root 6. So this becomes root 18 over 6 root 36. So what's the square root of 18? Simplified, that's root 9 times root 2. And 6 root 36, that's 6 times 6 because root 36 is 6. So this is then root 9 is 3 times root 2. 6 times 6 is 36. My final, or my next result, I should say, is 3 root 2 over 36. Now I want to think about this. Can this fraction be reduced? 3 over 36? Yes, it can. Its common factor, or greatest common factor is 3. 3 divided 3 is 1. 3 divided 36 is 12. So my final answer is 1 root 2 over 12. But I never want to write that. I just want to write root 2 over 12. Okay. Now, a second way to look at this is fine to reduce this fraction at the end because this numbers are easy. But let's rewrite this and sort of look at it a little bit differently. And you can do it whichever one is easier for you. So I'm simplifying this radical. When I have two radicals that are a fraction in the numerator and denominator division, I can feel free to put them under the same, and all I did was just put the coefficients here, made this a 1, as 1 and 6, and I can feel free to put them underneath the same radical. So that's the property of division of radicals that Mr. Duncan covered on Monday. For that reason, when I put them underneath the same radical, I can reduce 3 over 6, and that 3 over 6 reduces to 1/2. So I am essentially doing now this problem, which I can then break up to make these numerator and denominator coefficients again. So this is 1 root 1, or just root 1, over 6 root 2. The reason why I've done this is because now I've eliminated my reducing of the fraction at the end and made it a little bit easier to deal with. So I'm doing this exact same process now, and then I'm rationalizing the denominator by multiplying by the radical that is in the denominator here. But I'm getting to my final answer right away in that what's root 1 times root 2? That's simply root 2. What's 6 times root 2 times root 2? That is 6 times 2, because root 2 times root 2 is 2. Or root 2 over 12. So note that I can use either method by pulling these under the same fraction and reducing this fraction right away, which sometimes is easier than multiplying and reducing at the end, because sometimes you're dealing with these unreasonably big numbers. Or I can just simply multiply by whatever initial radical appears in the denominator and then simplify afterwards. So you have to decide which one's easier for you, but you should have both solution methods under your tool belt. And I know Mr. Duncan covered this on Monday. This is a perfect example of one where it doesn't make sense to multiply 14 times 14, and that 6 times 14 ends up being a really big number that's hard to deal with. So instead, what I'm going to do is bring this underneath the same radical, in that this is just, these coefficients are 1, so this is like a 1 over 1 here. So you don't need to write that, but you should identify and know that you're still dealing with the coefficients if there happen to be them here. What's 6 over 14 reduce? That greatest common factor is 2. So for that reason, this is 6 divided by 2 is 3. 14 divided by 2 is 7. So now I can feel free to change root 6 over root 14 into root 3 over root 7 for that reason. Rationalizing this denominator by multiplying by root 7 over root 7, I get my result, root 21 over 7. That is a final result because root 21 cannot be fully simplified. So in these problems, and we didn't see this from the odd problems from this review sheet how they happen to be, but always note that at the end, you are making sure that your coefficients that represent, or this coefficient, the radical, and the denominator doesn't represent a fraction that you can simplify. And also, you have to make sure that the radical and the numerator cannot be simplified. In this case, it doesn't need to be. Root 21, there's no perfect square factor, so this is my final answer. Okay, hopefully you got a lot out of this video. Feel free to ask me any questions via Edmodo. I'll be checking it tomorrow as well too, and I'll try to answer any questions you may have. Otherwise, you can come to me during the school day. Tomorrow I'm not going to be around after school, but I will be around during the school day tomorrow, Friday morning. You can prearrange with Mr. Duncan or myself to, come for some extra tutoring during tomorrow any lunch, but you need to prearrange with Mr. Duncan and either morning. It turns out that tomorrow morning might work. There's a chance for myself. Possibly Mr. Duncan would be available. Hopefully you would have prearranged that if you had done that. But certainly Friday morning, if you talk to us during the school day tomorrow, would work too. Okay. Good luck studying, and I'll see you in class on Friday.